As I've said before, one of my favorite topics in all of science is Einstein's theory of relativity, the intricate interplay of space and time into a glorious structure that we can understand and that upends our notions of reality in lots of cool ways. To understand that, I've been talking about using space-time diagrams with the help of special fancy hyperbola graph paper developed by Tom Moore at Pomona College, using this to visualize quantitative answers to questions about relativity without having to do a bunch of equations along the way. And previously, I talked about the fact that if I have this diagram drawn in Alice's frame, where Alice is sitting still and her path is just x equals 0 all the time, just on the t-axis, and I draw Zach's path, where Zach is moving at 2/3 of the speed of light, Zach's path going up along here, if I draw Zach's path, I can understand how Zach himself measures time along his journey by calibrating his path using these hyperbolas. You can see how that calibration is on here now, where the 1-year hyperbola intersects Zach's path here, the 2-year hyperbola intersects Zach's path here, the 8-year hyperbola intersects Zach's path here, and that calibrates Zach's own experience of time. What I want to do now is talk for a minute about how I can go beyond just Zach's own clock to talk about how Zach believes time works throughout the entire universe, how Zach would order events and measure the time between events everywhere in space, not just along his own path. And to do that, I'm going to have to think kind of hard about how someone could set up, could calibrate distances and calibrate times to distant events. Because even for Alice, whose graph this is, Alice who's sitting still, and this graph is in Alice's reference frame, not from Alice's perspective, even for Alice, we might want to have a method for doing that in a careful way. So let me talk about the method for doing it for Alice, then we'll show how that applies to Zach, and then we'll kind of stare and say, whoa, because it's weird. Here's the idea. Alice is going to use a radar method to figure out what events happen at Alice's own time equals 0. And here's how she can do it. Alice is going to send a radar pulse of light away from her position at, let's say, time equals -2 years on this space-time diagram down here. Alice is going to send a pulse of light out from there. Now we know it's light, and light travels at the speed of light, 1 light year per year, and so that's a 45-degree angle on these space-time diagrams where time is in years and position is in light years, or where time is in seconds and position is in light seconds, matching units in any case. So we know that the light's going to go out here, this way. Now here's the trick. Since it's moving at the speed of light, if Alice sees the reflection of that radar pulse return to her at time equals +2 years, then she'll know that whatever it reflected off of, it must have gone 2 years of travel out and 2 years back. And whatever it reflected off of, the reflection must have happened at time equals 0, exactly between the two, because with the same speed out and back, because it's light, always the same speed to all observers, and we know it would have come back to her at that same 45-degree angle, coming back this way. So if I want to know where that reflection was, that we know that Alice would know was at time equals 2 years, I can just follow the 45-degree angle up. Follow it up, and follow this 45-degree angle back, and we'll see that they met at this point here, 2 light years distant. Not surprising, right? The light goes out for 2 years, a distance of 2 light years, reflects and comes back. The time when it reflected was exactly in between. Time equals -2 years and time equals +2 years. So that point is a point that Alice knows is at time equals 0. She also knows it's at distance 2 light years, because that's sort of by definition. You can get both this way. Similarly, if Alice had sent a radar pulse out at time equals -1 year, and she got its reflection back at time equals 1 year, if she did that, then she would know the event it reflected off of was at time equals 0. If she had sent a light pulse out at time equals -4 years, and that was supposed to fit there, and it came back at time equals +4 years, she would know that that event where it reflected was at time equals 0, exactly between the two. I hope you get the idea here, that we're just finding these symmetric points, and in between, we're constructing a list of points that happen to be at time equals 0, as seen by Alice. This shouldn't be a complicated idea. This shouldn't be something subtle. It should seem pretty simple. No, it's actually the most cumbersome way of drawing the x-axis that you've ever seen, just doing this over and over. But I hope you get the idea that that shows us all the points, that this method will be guaranteed to show all the points that Alice would think occurred, all the events that Alice thinks occurred at time equals 0. If you're good with that, then we can take this over to look at what Zach would see for the same process. And so we're going to come over to Zach's path, which we've calibrated nicely. And now, ideally, I guess, I would take Zach's time equals minus 1 year and Zach's time equals plus 1 year and do things there. I want to use my grid a bit more. So instead, I'm going to take the point along Zach's path that Alice would have said was minus 3 years. This one. Now, for Zach, that's minus 2.2, maybe 2.1, something like that, years. And the point that Zach would say is 2.2 years positive, but that Alice says is 3. Since the line goes straight through that, it'll be easier to use my graph paper for that. It's the same thing. It's a matching thing. Minus 2.2 plus 2.2. It'll just help me out. I want to send light rays out at 45 degrees forward in time from here and from this point, and then I want to extrapolate backward in time from this point. Remember, light rays can go either in the plus x direction, forward in time going to the right, or the minus x direction, forward in time going to the left. So I'm going to say, I know it's going to reflect off some path like this. It's going to go 45 degrees, 45 degrees. I want to follow both of those and find where that reflection point would have been. Let me do that. And again, 45 degrees is easy to see on the square parts of this. I'm going to ignore the hyperbolas for now entirely. So what I have, I'm going to start, let me line this up. I'm going to start at minus 2.2 and run forward. Let's see where that takes me. My minus 2.2 running forward 45 degrees. Got to get 45 degrees just right. Something like this. There's the light ray going out from Zach's path at minus 2.2. And then at plus 2.2, it must have bounced somewhere so it gets back at plus 2.2. So let me work backward along this 45 degree angle to see where that must have come from. Make sure I get this angle right. Don't want to mess that up. Angle right. It looks like it came from this point here. That's not on the x-axis. That's already weird. Let me try another one. Let me try Alice's 6-year mark, which for Zach is about 4.5, and minus 4.5 down here. Let me try the same thing for that to see what I come up with. Again, I'm going to line this up. I'm going to go along from this point that's the minus 4.4, minus 4.5, whatever, Zach's calibrated point, but Alice has minus 6. I'm going to go from here, and I'm going to go up as far as I need to. Let's see what we have. So there's the light going up from here, from Zach's minus 4.4, and it must reflect off of something and come back over to the plus 4.4, 4.5, whatever, to this point. So I'll work backward from there, find where that intersects. Again, I'm going along the diagonal here because that makes my life much easier to draw. It looks like this point is an intersection point there. Again, not on the horizontal axis that Alice would have said was time equals 0. Alice would have said that this was the time equals 0 point for all events in the universe. Anything on this line was time equals 0. I like to call that a time slice, a slice of time for Alice, the time equals 0 time slice, or this would be Alice's time equals 10 time slice up here. Where is Zach's time equals 0 time slice? Well, look at this, actually. Let's look at this. It appears that these dots and the origin, this is clearly time equals 0 for Zach, because we defined that to be Zach's time equals 0. The origin, these are all on a line together. Let me connect the dots, which seems like a fun game to play along the way. Let me connect the dots and see where this takes me. See what I end up with here. Connecting the dots. I want to make sure that it goes through the origin. Make sure I don't mess that one up, of all things. Okay, let me just do some dashed lines. I'm doing a dashed line to represent Zach's time slice here, going along the universe. This dashed line, I hope you can see it, goes through time equals 0 here, goes through this point that Zach would have said was time equals 0, this point that Zach would have said was time equals, because remember, Zach sent out a radar pulse at minus 2.2 years, and it came back at plus 2.2 years. Zach is going to say the event it reflected was at time equals 0, right between minus 2.2 and plus 2.2. Zach's going to claim that. So this dashed line, dashed line is Zach's t equals 0 time slice. I'll put a little t equals 0, labeling that dashed line for Zach. That's weird. This is weird in relativity. That the points that Zach thinks happen at time equals 0 years are not the same as the points that Alice thinks happen at time equals 0 years. It's a strange thing that that's the case. And we have to really make sense of this. This is not easy to make sense of. It means, for example, that if Zach and Alice have a friend, Murray, and Murray has a birthday party at this event right here, was Murray's birthday party, did that happen after Zach passed by Alice? Or did that birthday party happen before Zach passed by Alice? Alice would clearly say it happened 2 years later, because Alice's time equals 2. So Alice would say the birthday party happened after Zach passed by Alice by 2 years. Zach would say, no, time equals 0 is all the way up here. Zach would say this birthday party happened, well, I can't measure exactly, we'll learn later how to measure the time, but Zach would say that point is clearly before, lower down on the graph is before, time equals 0. So Zach would say that the birthday party was before Zach passed Alice. That's a weird result in relativity. In general, in relativity, two observers may not agree on the order of events if those events are at far distant separated places in space. The order of events may be something people disagree on. In some cases, there's a whole complicated story on when they will and when they won't, but that's the core idea. So that's a neat concept that that's true. What can we learn from this? What can we do to make sense of this? Let me tell you some other things about this calibrated path, about this time slice rather. One of them is, just like I said over here, we could use this to tell this method for Alice to figure out where the 2 light years was, 4 light years. You know, if light goes for 4 years and then comes back 4 years later, that event where it reflected must have been 4 light years away. We can do the same thing along here with this dashed line, this time slice. And in fact, we don't even need to do, oh, this is minus 2.2 years, so this must be 2.2. We can actually use the hyperbolas again. It turns out, you can argue it to yourself using the space-time interval equation, but it turns out that everywhere that this time equals 0 time slice crosses a hyperbola, this only works for lines that go through the origin. Remember, these hyperbolas are drawn with the origin being one end here, being the central point. So for this, but since this time equals 0 time slice goes through the origin, we can use the hyperbolas to calibrate it. And so every time it crosses a hyperbola, that's going to be another step along, another light year along. So here, for example, would be 1 light year. Here, where it crosses the 2 hyperbola, would be 2 light years. Here would be 3 light years. The 4 light year hyperbola crosses this dashed line here. There's 4 light years. You get the idea. We can calibrate Zach's idea of distance as well by marking hyperbola intersections along Zach's time slice, t equals 0 time slice. Again, once we've done that, we erase the hyperbolas from the entire graph paper. Once we've calibrated these two things, the hyperbolas are only useful for calibrating Zach's path in his time along his path, and calibrating Zach's idea of distance along that t equals 0 time slice. Those are the two things we can use the hyperbolas for, and then we're done with them. But that gives us an idea. So, for instance, if I look at this, how about this point right here? At this point, Alice would say that this point is at time equals 4 years and distance equals 6 light years. At this point, Zach would look and say, no, Zach would say at that point is only a distance of maybe 4.5 light years from the origin where he left. Only a distance of 4.5 years. What time is it? Time equals 0, because this is a time equals 0 time slice. So they'll disagree on those coordinates, but they'll agree on that is the event where this reflection took place. That anything that happened at that place, the two will agree on. The other thing to notice, and this is actually the most useful thing for these time slices, it would be a pain if we had to draw these lines every time, these reflections every time to make that time slice. It actually turns out, by a miracle of mathematics, or by the structure of space and time, more to the point, it turns out that we can figure out what angle to draw this time slice at, the time equals 0 time slice, easily. All we have to do is this. Whatever angle down from vertical Zach's path is tilted, that is the exact same angle up from horizontal that Zach's time slice is tilted. You can see it in here, right? In fact, we can even count it. This is 2/3 light years per year. 3 years up, 2 light years over, right? This is 3 years over, 2 light years up. 3 years over, 2 light years up. 3 years over, 2 light years up. That's how the time slice works. It's exactly the inverse of the slope of the path itself. And so the faster you go, the closer to the speed of light you come, the closer to 45 degrees you come for your path, the closer to 45 degrees your time slice comes as well. If you're sitting still, they're perpendicular. But as you go faster and faster, they come closer and closer together. And as you approach the speed of light, they both approach 45 degrees. That, to me, is a really cool thing about how these time slices show up on the diagram. And the beautiful thing is that if you know how to draw this path, you can draw the other thing, and with the hyperbolas, you can calibrate both to get Zach's idea of time and Zach's idea of distance onto the diagram. And those are the building blocks that we'll use to do all the other things that we do with space-time diagrams. Once you have those two pieces, you can use this to understand all sorts of complicated questions in relativity without using equations. All you need is just the diagram and these two calibrated things, the path and the t=0 time slice. And you can do all the calculations you want to just by drawing lines on some paper. It's pretty cool. I hope you find it useful, and I hope the other examples we do are useful to you as well.